This video is going to be historic in this series for a few reasons. First of all, we're finally done with derivatives. We're going to go on to integrals. Now, that doesn't mean we're going to stop talking about derivatives. Far from that, actually. The next few videos, we are going to talk about derivatives. It's just, this is specifically focused on integrals. Second, this one is going to be probably the longest video of this entire series. Maybe the last video might be a bit longer, but this one is definitely up there. We're going to talk a lot about integrals. And the last reason is because this is the first video with a few BC only topics. They're going to occur at the end of the video. So if you're AB, just skip over that, skip to the practice questions. But like I said, this one's going to be a long content review, so we better get right into it. Okay, first of all, we're going to talk about what is called the accumulation of change. And that's basically, well, that's half of this unit name. It's integration and the accumulation of change. Accumulation of change is basically the signed area under a function. What does signed area mean? So let's say you have a function like this, right? The area of a function is basically just going to be the sum of the different areas. But the signed area says that the area above the x-axis is positive and below is negative. So it takes the sign of the area into account. And just like with anything else, just like with limits, just like with derivatives, this can be determined graphically, numerically, or analytically. We're going to focus on graphically and numerically now and go into analytically later. And how exactly are we going to determine this graphically and numerically? We have to estimate it, of course. And we're going to use what are called Riemann sums. Riemann sum is basically a sum that approximates the area under a function using a bunch of shapes that are easy to find the area of. So let's say you have a function like that. There's going to be different types of Riemann sums we're going to use. But the basic principle is that over an interval a to b, it splits it into n different shapes with the width of each shape being b minus a over n. And usually they're going to be rectangles. There is one counterexample to that, but usually going to be rectangles. Now, the first type is called a left Riemann sum, or left endpoint Riemann sum. And that's where the rectangles have the left endpoint on the graph itself. So this is an example of a left endpoint Riemann sum. As you can see, it kind of underestimates the area of the graph, but that's only because this graph is increasing. If it was instead decreasing like that, left endpoint would overestimate it. But yeah, that's good to know as well. But the left area formula is going to use summation notation. It's going to be from I equals 0 to n minus 1 of the width delta x of each rectangle times the height of each rectangle. So that's going to be the left endpoint, the value of the function at that left endpoint. Now it starts at a, then goes into a plus delta x, because delta x is the width. You're just going one width away. Then a plus 2 delta x, 3 delta x, 4 delta x, and so on. It would be nice if we had a way to count this, starting with 0 delta x to 1, 2, 3, 4, and so on, all the way to n minus 1. That's exactly what the bounds are here for. And so it's just going to be a plus delta x times I in here. And then we have the end of the summation. And the summation just adds up all the rectangles. And so this is going to be left endpoint. There's also going to be right endpoint. And surprisingly enough, the argument of the summation is going to be exactly the same. The only thing that changes, though, is the bounds. It's going to be from 1 to n instead of 0 to n minus 1. And this is similar, except where the right endpoint is on the curve instead of the left endpoint. There's also midpoint, where the middle of the rectangle is exactly on the curve. And it's going to be, you can do from 0 to n minus 1 of delta x times, now the argument is going to change, it's going to be f times, f of a plus delta x times I plus 0.5. You're adding half of I back, half of the width back, because you're going to the middle, not just one of the endpoints. And finally, there's the trapezoidal rule. This one, we're not going to use summation notation, but it's basically saying if you break it into trapezoids of equal width, delta x, the area is going to be delta x over 2 times the function value at the first point plus 2 times the function value at the second point plus 2 times the function value at the third point, and so on, all the way until 2 times the function value at the last but 1 point. So you can write it as b minus delta x plus just the function value at the last point. And so all of these terms have 2 except for the first and last terms. So that's what the trapezoidal rule is. And that's it for our approximations. You can use this both graphically and numerically. Graphically, obviously, you can draw rectangles, calculate it, less common. Numerically, if you're given a table, you can write a Riemann sum. Obviously, not with a summation notation. You would just add them up physically, because you'd be given values in a table, and you can draw it, I guess, or you can just think about it in your head, visualize it, and see that, oh, if it's going to be a rectangle, you're going to need to use these values, and so on. But that's enough of approximations. We want to get exact answers. We want to do it analytically. And that's why we're going to introduce what's called a definite integral. Finally, we're going to talk about integrals. And the definite integral basically finds the exact value of the signed area under a function. And the reason why it's called definite is because it's defined over an interval. There's a specific interval that you use, a to b, with the lower number being the lower bound and the higher number being the higher bound. And you have f of x as the argument, and you always end it with dx or d whatever variable, du, dy, whatever. But that dx symbolizes a really, really, really super thin slice, right? Basically, instead of doing entire rectangles, you're doing very thin slices. Basically, the width of the slice is essentially 0. In fact, you can say it approaches 0. That should ring a bell right there. As something approaches a value, right? That is just limits. We're going to get back to limits. Now, instead of doing limit as delta x approaches 0, instead we're going to do limit as n approaches infinity. Because n is just the number of a rectangle. So if that approaches infinity, then delta x approaches 0. Now, just for space, I'm going to move this down here. And now, what do we write in here? Well, of course, we write the Riemann sum. Now, you can use either left endpoint, right endpoint, or midpoint. It doesn't really matter because, at really thin slices, there is practically no difference between the value of the function at the left endpoint, at the right endpoint, or at the midpoint. I'm just going to use right endpoint, and you just have the argument of the function in there. That's going to be the official definition of a definite integral. The limit as n approaches infinity of this Riemann sum. And so with that in mind, what can we do? Well, first we said a function can be differentiable. We can also say a function can be integrable, meaning the definite integral exists. And the rules for this are very, very relaxed, right? It doesn't even have to be continuous to be integrable. You can have a function like that, and to find the area on this interval, you just find this rectangle and this trapezoid, and you can find the definite integral. That means that basically, well, practically any function has a definite integral. Basically, every function is integrable. But you still need to include that because, it's fancy language and it actually means something. Okay, and the last part of this first part of the video. Again, this is going to be a really long one, so be prepared for that. We're going to end off with some properties of definite integrals, and then we have a whole nother section to talk about. But there's 6 main properties you should know. Some of them are pretty trivial. Some of them are actually take some time to think about. But first one is, if both the bounds are the same, the area is just 0. And that's because it's just a thin slice. It doesn't have an area. Second one is that you can switch the bounds, right? You can go from b to a instead. But if you do, you're going to have to negate it. It's going to be the negative of. Third one says the integral from a to b of f of x plus or minus g of x dx. You can just split it into f of x dx plus or minus g of x dx. Right. Also similar to derivatives. And yet another similarity to derivatives. If you have a constant in the function, you can take that constant out. Just like derivatives. Okay, and then these last two are also pretty important, but pretty long as well. First, if you have just an ordinary definite integral, you can split it at some point c in the interval. And if you do this, you're going to get the exact same area. A to c and then c to b. You're going to get the same exact area. And that just comes from the geometric definition of area. If you have two areas together and you just add them, you're going to get the total area. And finally, the most complicated one, you can shift the bounds or the function of an integral, but if you do, you're gonna have to shift the other. If you add some value h to both bounds, you're gonna have to shift the function x minus h instead. So if it's like f of x minus 2, you're gonna have to add 2 to the bounds, and so on. So these are the 6 properties of definite integrals that you should definitely know, definitely memorize, and definitely know how to use. And that wraps it up for this first part. And I am going to have to erase it now, so if you didn't catch all of that, be sure to go back and pause it. But the reason why I have to erase it is because we have a whole nother part to this. And I might even have to erase it one more time because that's just how long this unit is. But now we're finally going to be talking about another type of integral. Now, you might have already guessed that because we had to specifically call this one definite integral. That implies that there should be something else. And you might have also guessed that this one's called indefinite integral. Right, you have definite, you have indefinite, obviously. And the indefinite integral is not on some interval. It's just there. You have integral of f of x dx. And this basically finds the antiderivative of a function, or basically undoes the derivative. We don't really have a special symbol for this, just like we have f prime of x, we have f double prime. We don't really have that for indefinite integrals. We really should, but all we do is we just capitalize the function, which seemed kind of pointless because if you already have a function that is already capitalized, like a profit function in a word problem, like capital P of x, what are you going to do then? But oh well, we have to use this. And we also have to add what is called constant integration C. It's just this arbitrary constant. You add it everywhere. You can have some actual function here. You still have to add plus C. And the reason why is because when you take the derivative of this new function, this constant term just cancels out. So you never know what this original constant term is. So you just keep it there. Unless they give you the initial value. Let's say they say find this indefinite integral and goes through the point 0, 2. Then you have enough information to solve for C. But in general, you want to find the general antiderivative, you have to add this plus C. There's one more property of indefinite integrals that we have to talk about. And it looks strikingly similar to a few properties of definite integrals. If you have something like this, a complex expression, you can just take out the a and then split the integral. Just like that. Combines 2 properties in one, multiplication and addition, subtraction. And then there's also one more rule. Remember the power rule for derivatives? There is going to be a power rule for integrals. It basically undoes the power rule for derivatives. And that's a common theme throughout. A bunch of techniques we're going to do is going to undo rules we learned about derivatives. So if you have the integral of x to the power of n dx, where n is a constant, remember, it's going to be equal to x to the power of n plus 1 over n plus 1 plus c. Looks pretty complicated. Don't worry about it, though. You can test this out by taking the derivative of this expression. You're going to get x to the power of n. Okay, we've reached that point in this pursuit of antiderivatives that I'm just going to throw a bunch of formulas at you. If you remember from derivatives, over 2 videos, I just threw a bunch of derivatives you should memorize. I'm going to do even more now. It's going to be a total of 16. Technically, it was 16 earlier, but it was just split up over 2 videos, so it's manageable. But now I'm just going to throw 16 at you. And they're not that hard to memorize. In fact, I'm not even going to write them down. I'm just going to say, do your homework, go back to your notes that you took on the previous videos, chapter 2 and 3, I believe, which talked about derivatives of common functions, and just look at those, and then undo them, add a plus c. I'll give you an example. We had sine of x goes to cosine of x, right? And so now you should write the integral of cosine of x dx. You basically take this answer is equal to sine of x plus c. Just the same exact thing, right? You just flip it around because the antiderivative undoes the derivative. The indefinite integral undoes the derivative. I'll give you another example. We had log base a of x goes to 1 over x times ln of a. In this case, we just write integral of 1 over x times ln of a dx is equal to log base a of x plus c. There's one small caveat when it comes to ln and log. You're going to have to put this x in absolute values because you cannot have a negative value inside a logarithm. when it comes to antiderivatives, because one more example even. Integral of 1 over x dx is equal to ln of x. But you have to do absolute value of x, because if you see the graph of 1 over x, you see there's an inherent problem, because you're going to get a negative answer here. And so you cannot have a negative, and so you have to restrict it to absolute value of x. So there's 16 of these. And if you go back and count the ones I gave you before, there should be 16 of them. Just do as I say, just flip them around, integral plus c. And don't forget the dx there. It's just as simple as that. That would take a long time for me to write all of them, say all of them, and things like that. But you should be able to get all of them. And you don't even have to memorize them, because you memorize them for the derivatives. You just have to undo them now. Okay, rant over. Now, we talked about definite integrals and we talked about indefinite integrals. They seem very connected. They use the same symbol. They both are integrals and so on. But what is the connection between them? That is going to be what the fundamental theorem of calculus is, the FTC. It has two parts, and it basically connects both derivatives and definite integrals. Or you can see it as it connects definite integrals and indefinite integrals. The first part tells us how to calculate a definite integral. It says the integral of from a to b of f of x dx is equal to capital F of x. Remember this from before. And you just evaluate it from b to a. And that's just going to be f of b minus f of a. And so this basically says, to find the definite integral, you take the antiderivative and just evaluate it from the top bound to the bottom bound. Easy as that. The second part is a bit more complicated, but also pretty useful. It says that if you take the derivative, d dx, of a definite integral with the variable in its bound. So this, I'm going to point out, is pretty important. You'll notice a few things here. First, this is t, not x. Inside this, there should be a different variable, and outside this, there should be a different variable. This x should be matching what is in this derivative, and this t should be matching what is in dt, right? It can be a different variable. It could be x here, but that means that it cannot be x here. That would mess everything up. And so this is just equal to f of x itself. But this basically tells us that the integral undoes the derivative. It shows how derivatives and integrals are connected. And then there's one more part, like an unofficial extension, is the chain rule extension of the fundamental theorem of calculus. Basically says the d dx of integral from, well, we had variables in bounds. Why can we not have functions in bounds? So from h of x to g of x, and then the integral of f of x dx, right? What's wrong with that? Well, there's nothing wrong with that. We just say this is equal to f of g of x times g prime of x minus f of h of x times h prime of x. Now, notice this looks a lot like the chain rule. That's why it's called the chain rule extension. Just, it's not f prime and f prime. And the reason why is because this is not f prime. This is just f. And so you're using that same thing again. It undoes it, so there's no more f prime here. But this is still g prime. Because d dx, and then you have a g prime of x here. That is not part of the actual integral. That's not part of the argument of the integral. And so that's still, you have to take the derivative of that when you substitute it in. So know those, pretty good to know. Okay, and then finally, this is, we reverse the power rule. Let's reverse the chain rule. This is basically integration by substitution. And that is a method, like I said, to reverse the chain rule. It uses a dummy variable, usually u. That's why it's called u substitution. And there are three main steps. As with a bunch of things we're going to learn, there are three main steps. First, substitute a new variable for the expression involving the old variable. So if you have something like, if you have f of x dx, right? You have something in terms of x. You want to substitute a new variable u in terms of the old variable. Let's say you have something like this, a very basic example, but you have x squared times x cubed dx. You can just simplify this into x to the power 5 and use the power rule. But let's say we don't want to do that. We can say this new variable u is equal to x cubed, right? We just substitute that in here. We need to write the rest of the expression then in terms of u and du. First, what is du? You take the derivative of this, that's going to be 3x squared dx. Don't forget the dx. That's because this is a different derivative. And so we see a 3x squared here, we see just an x squared here. And so we see an x squared dx. Well, that rings a bell. X squared dx is just going to be 1/3 of du, because du is 3x squared dx. This is just x squared dx. And so what you can write this as is integral of u, you have that u, but you also have that 1/3 du. And if you see, everything else is gone. There is no more trace of x. And so rewriting this, you see it's equal to 1/3 of the integral of u du. And you can use some basic power rule stuff to find out what the antiderivative of this is. This is just u to the power of 1. So using the power rule stuff formula, it's u to the power of 1 plus 1, which is 2 over 2. And then we have that original 1/3. So that's going to be equal to, don't forget the plus c. You have u to the power of 2 over 6 plus c. And so that was the second part. Rewrite the integral and bounds in terms of the new variable. Third part, find the integral. And then you have to rewrite the result of the integral in terms of the old variable. So you have to replace this u with x again. And we said u is x cubed. And so this is going to be x cubed squared, which is just x to the power of 6 over 6 plus c. And if you had used just the power rule, you would have gotten the same answer. And for you AB students, that's it. That is this entire unit. For you BC students, unfortunately, there's going to be a few more complicated topics we're going to have to go through. But AB students, feel free to just skip to the practice problems. A lot of those practice problems actually are BC only. So there might just be a few that apply to you. But BC students, you're stuck for a few more minutes about this. There's 3 topics that are BC only. First is integration by parts. Now we saw how we can reverse the power rule, we can reverse the chain rule. We're now going to reverse the product rule. And in very basic terms, this basically says that the integral of f of x times g prime of x dx, right? You have a certain function, and you also have a function that is the derivative of another function. This is equal to f of x times g of x minus the integral of f prime of x g of x dx. That looks very complicated, yes. But let's say, I'll show you an example when we do practice problems later on. But let's say you know that this is a certain function, this is the derivative of a known function. Well, you just use the original function times the known function you had before, and then the derivative of the original function times the known function you had before. Another way you can think of it, let's say u is equal to this f of x, and dv is equal to this g prime of x dx. That means du is equal to f prime of x dx, and v is equal to g of x, right? And you create a number 7. It starts like this: u times v, and then you go down here, and there's a minus sign. This middle segment right here is a minus sign, indicating that u minus. And then there's this segment from v to du, so it's integral of v du. That's basically what this part above says. Again, I will show an example later, but just know how to do this. And then we get into integration by partial fractions, or also known as partial fraction decomposition. And this is definitely best done using an example. But basically, you're decomposing a rational function into the sum of 2 rational expressions with linear denominators. So let's say you have 1 over x squared minus 3x plus 2 dx. Now, if you took algebra, you should automatically think of how to factor this denominator. You get 1 over x minus 2 times x minus 1 dx. But how do you find the integral of this? You can rewrite this as the integral of a over x minus 2 plus b over x minus 1. This is, the first step was factor the denominator. Done. Second step, find the constants in the numerator that make the sum of the new rational expressions with linear denominators equal to the original rational expression. So you have to find the values of a and b to make them equal 1 over this. And you just use a system of equations. You say this is equal to that. You multiply everything by the denominator, and then you group the terms that just have x, you group the terms that are just constant, and then you solve for a and b. I will show an example of this later on. But once you've solved for a and b, then all you have to do is just find the integral of this new function. Let's say you have a certain a and b value. You find the integral of the new one using the fact that integral of 1 over x dx is equal to ln of absolute value of x. And then you use properties of logarithms to simplify everything. Okay, and final topic for UBC students, improper integrals. And that's basically when either the function or the bounds approach infinity. You can have something like 1 to infinity of 1 over x squared dx. You can also have something like negative 1 to 1 of 1 over x squared dx. Both of these are both improper integrals. This first one actually has infinity in its bounds, so it's pretty obvious that it's improper. The second one doesn't, so you might just try to apply, like actually take the integral of this. You'll get surprising results though. And the reason why is because the value 0 is on this domain. And if you plug in 0 in here, you're going to get 1 over 0 undefined. It's basically going towards infinity because 1 over x squared just looks like this. And remember I said when basically all functions are integrable? This is basically the exception, right? You cannot technically take the definite integral over this interval. And so what you have to do is you have to rewrite the integral as a limit of a definite integral with the variable and the bound as the variable approaches the original value. So you can say limit as a approaches infinity of integral from 1 to a of 1 over x squared dx. And now you just evaluate whatever's in this argument. You just find the antiderivative of 1 over x squared and plug in a, plug in 1, subtract them, get an expression, and then just take the limit of that as a approaches infinity. Similarly, over here, you can do limit as a approaches 0 of negative 1 to a of 1 over x squared dx. But that means it's only from negative 1 to 0. We want it to be from negative 1 to 1. So you have to add integral from a to 1 of 1 over x squared dx. This is where our previous property of definite integrals, the fifth one, comes in handy. You can break an area into two different areas. Again, this is a bit more complicated than the previous one, but it's basically going to be the same steps. And yeah. And now even you BC students, that is going to be it for the content review. And we can jump right into our practice problems. I'm glad that all of you guys stuck with me all this long because this was definitely one of the longest videos we're ever going to record. Let's start with this first one. It's a pretty simple equation. I mean, okay, no, it's actually not a simple equation. I take that back. But we see something immediately. We see a sine and we see a cosine. What can we do? Well, we know that the derivative of sine is cosine and the derivative of cosine is negative sine. What can we do there? Well, if we say u substitution, right, that's obviously going to be the first thing on your head because we just learned that first of all. And second of all, we see a function and its derivative. If we say u equals sine x and say du is equal to cosine x, that runs into some problem because we cannot have square root of 1 plus du. Du has to be on its own out there. So we can say u is equal to cosine x and du is negative sine x and just make this negative du is equal to sine x. And that works. One thing to note is the bounds here. Keep an eye on that. Let's ignore the bounds for a second. We'll bring them back later. But remember that negative sign from the du. And then we have just 1, or du technically. We do have du in the numerator over square root of 1 plus u. And nothing else. And then we can just move this du here and just 1 up here. Now what do we do with the bounds? Well, instead of just doing 0 and pi here, we have to make sure that the bounds actually match the function that we substituted in for. So we have to plug in 0 into u. So cosine of 0, that's going to be equal to 1. And then cosine of pi, that's going to be equal to negative 1. Looks a bit weird, but we can still solve for it. In fact, we can even get rid of this negative and make it from negative 1 to 1, simplifying the expression and also simplifying the bounds. Because, like I said before, with the properties of definite integrals, you can swap the bounds, but you have to negate it. Okay, this looks a bit weird, definitely. But you can basically kind of do another u substitution. Like if you want to think of it intuitively, if you've done enough integral problems that's not a problem for you, you can just do it straight from here. But you can technically do another u substitution. This time, let's say a v substitution. We say v is equal to u plus 1, and so dv is just equal to du. And so this is equal to integral, and this is actually going to be from 0 to 2 this time, of 1 over square root of v dv. And now it becomes pretty easy to solve because instead of 1 over square root of v, we can just write this as v to the power of negative 1/2. And now power rule, this is going to be equal to, you have negative v to the power of negative 1/2 plus 1, which is 1/2, over that, which is 1/2, and from 2 to 0. So that's just going to be equal to 2 root v from 2 to 0. You plug in that, you get 2 root 2 minus 0, or just 2 root 2. And that's going to be your answer. Now, you can, again, if you haven't done many integral problems before, you might not think of doing u substitution at first. But in the end, you're going to need to do u substitution because you have cosine x and you have sine x. That is basically the only way to solve this without using a calculator, and you're going to need to get used to doing some integral problems like this. Okay, moving on to the second question. This one looks a bit more complicated, and it is. We see this and we see that. You might think u substitution, that might get us somewhere. In fact, if you say u is equal to 1 over x, which is a pretty nice substitution, that's just x to the power of negative 1. You take du, that's going to be equal to, you bring down the negative 1, and then subtract 1 from the exponent. So negative x to the power of negative 2, or negative 1 over x squared dx. That's going to be this. And so u substitution is the way to go here. You can also use integration by parts, but I would not suggest doing that. And so you have integral of negative du, again, because this is negative 1 over x squared, this is just 1 over x squared, times secant squared of u. And no, we do not have a du then because there's already a du here. So this is just negative integral of secant squared u du. Now, remember when I told you to copy down those 16 antiderivatives? You should have done that. I really hope you did do that, because you see that secant squared is a common antiderivative. Or, if you remember the derivatives, you notice that the derivative of tangent is secant squared. And so, the answer to this is just negative tangent of u plus c. That's not our final answer, though, because u is equal to 1 over x. And so this is going to be negative tangent of 1 over x plus c. That would be your answer. Okay, moving on to the third problem. How do we solve this one? Now, BC students are probably yelling at their screens, partial fraction decomposition. AB students probably have no idea what that is because they just skipped the section about partial fraction decomposition. Now, you're not going to use partial fraction decomposition for this. You can try your hardest, but you will not find factors for x squared plus 2x plus 10. It looks deceivingly like partial fraction decomposition, but unfortunately it is not. In fact, all three of these are going to use the same topic, u substitution. This one is just straight u substitution. This one looks like it could be integration by parts. Again, AB students, don't mind me in this section right now, but it is u sub. This one looks like it should be partial fraction decomposition, but it's just u sub. Let's see how that works. While you cannot factor this, you can complete the square. You can write x squared plus 2x plus 1 plus 9 dx. That's equal to integral of 1 over x plus 1 squared plus 9 dx. What do we do from here? Well, u sub, u is equal to x plus 1, du is equal to dx. Just as simple as that. So it's going to be 1 over u squared plus 9 du. Now, you're going to need to know something very specific here. The integral of 1 over x squared plus 1 dx is what? Again, you should know this because of the formulas you should have copied down. It's equal to the inverse tangent of x plus c. Okay, well, in this case, it's just u. But we have a 9 here instead of a 1. Well, if you replace this with any a squared instead of 1 squared, it's just going to be x over a. And then a 1 over a in the front. You should know this by heart. Or at least you should know how to derive this or something like that. How to get this. Because it's pretty common to see an x squared plus 9 or x squared plus 4 in the denominator. You should know how to solve for that. I won't show that here because we are running very late. It's past 30 minutes already. But you should know that this is equal to that. And so this is just going to be equal to 1 over 3 times the inverse tangent of u over 3 plus c. And we know u is equal to x plus 1. We just substituted that. So our answer will be 1/3 times the inverse tangent of x plus 1 over 3 plus c. Nice. Okay, now AB students, that's the end of the video for you. You will not know how to do this last question. BC students, stick around. We have to do this last question. This is improper. This is obviously an improper integral because there is an infinity in the bound. What can we do? We can say limit as a approaches negative infinity of integral from a to 0 of 1 over 4 minus x squared dx. We can do something a bit further though. U sub. Again, all of these problems use U sub. You can say u is equal to 4 minus x, and so du is equal to negative dx. And so we just have this extra negative sign. We have a du now, and this is now u squared. Now what would the bounds be? Well, 4 minus 0 is equal to negative 4. Is equal to positive 4. And then 4 minus a is equal to 4 minus a. And so what is the integral of negative 1 over a u squared? Well, you could use the anti-power rule. You're going to get it's equal to 1 over u itself. And so this is equal to limit as a approaches negative infinity of 1, basically just 1 over u. There's no more negative sign. And it's from 4, and 4 minus a and 4. So you actually plug this in. First you do the 4 up, and then you subtract 1 over 4 minus a. And what is this equal to? Well, this first term doesn't have any a in it, so you can just take that out. Minus the limit as a approaches negative infinity of 1 over 4 minus a. Well, as a approaches negative infinity, negative a approaches infinity, which means 4 minus a approaches also infinity. So this is basically 1 over infinity, which is technically mathematically incorrect, but that's just equal to 0. And so it's just 1/4 minus 0 or 1/4. Your answer to the improper integral will be 1/4. And that is all for this video. This, again, was the longest video. Probably the 3rd or 4th time I've mentioned that. But it is important. Unit 7 is going to be much shorter. And then 8 is also mediocrely long. 9 is pretty short. 10 is also pretty long. But this is probably the worst video by far. Lot of content, basically all of integration in one. And then there's applications of integration later. But yeah. So thank you for sticking with me through the end, and I'll see you in the next.